we don't need to have something like benzene in order for it to be aromatic. Also, the number of p orbitals and pi electrons do not need to be the same. They happen to be so in those neutral molecules with just carbons, but let's introduce ourselves to some different substances. So let's start with cyclopentadiene, 5-membered ring with just 2 double bonds in it. It is non-aromatic, right? We can't even compare it to these other things because the system of p orbitals is interrupted by an sp3 carbon. I guarantee you that's something that a lot of students miss. If we have a carbon that is just single bonded in that ring, it's sp3, and we have no p orbitals to advance that overlap around the ring that way. So there is our sp3 carbon right there. So we can't even compare it. It's non-aromatic. Okay? Doesn't count. But if I remove one of those hydrogens, I can rehybridize that carbon, and that can happen in one of 3 ways. If I take a hydrogen and its electrons away, so if I remove a hydride, I get a cation. So I get a plus charge along that 5-membered ring. If I take an H away along with one of its electrons, I get a radical. If I take away just an H and leave the electrons, I get an anion. So in all of those cases, we end up with a compound that's been rehybridized, so it has p orbitals now on all of the carbons, right? And a single H on each of the carbons. But what we're determining is whether that 5th p orbital there is empty, has 1 electron, or 2 electrons within it. Okay? So Huckel's rule, that's 4n plus 2, right, where n is 0, 1, 2, 3, 4, predicts that the compound with 6 electrons will be the aromatic one, because if n equals 1, and n can be just 0, 1, 2, 3, 4, if n is 1, that's just 4 plus 2 is 6. Okay? So that predicts that that'll be the aromatic one. We can see that experimentally. It's very simple to deprotonate cyclopentadiene, right? If I deprotonate it, I remove just the H and keep its electrons there to make the anion. Here is the 2 electrons right in there. And what we end up with is electron density evenly spread throughout all of those 5 carbons. Cyclopentadiene is really very acidic. It's pretty much one of the most acidic hydrocarbons that there is. It's almost as acidic as water, pKa of around 16. So hydroxide even will deprotonate cyclopentadiene to some extent. We can see through resonance structures how that negative charge can be distributed through the ring, dot, dot, minus, because what I can do is put those 2 dots down into a double bond. I can make a new negative charge right there, so dot, dot, minus. Do the same thing with those. Leave that first one alone, dot, dot, minus. I can go around again, right? I don't have to draw all these, but we can draw resonance structures with the minus charge on all of those 5 carbons, so it's evenly distributed between all of them. So we can see that through resonance picture. That's sort of old-fashioned. The better way of seeing it is with the molecular orbitals, which we'll draw in a second. There's a similar situation for cycloheptatriene. If I have a 7-membered ring with 3 double bonds, right? Here's our non-aromatic cycloheptatriene, because here is our sp3 carbon. Right? What I can do, if I remove an H as well as its electrons, what we can end up with is a cation, where I have an empty p orbital on one of those hydrogens. I can, through resonance, distribute that positive charge through all the entire every carbon with that ring. We see that in this electrostatic potential map, that it's symmetrical. Okay? By removing those electrons, we have 6 pi electrons around the ring. That again gives us an aromatic system. And through molecular orbitals, we can see how that works. The 5-membered ring before, okay, here's our 5 molecular orbitals. The cation, okay, where I just had the 2 double bonds. Here, let's draw them. 2 double bonds and a plus. Right? That only has the 4 electrons. There we have 2 radicals. So that's anti-aromatic. Okay. The radical has paired on the bottom, paired on one of them, but then a radical in one of them, just like we would imagine. Yeah, that's radical. Yeah, it's not aromatic. But the 5-membered ring with 2 electrons in that empty p orbital, which gives it a minus charge, has 6 electrons, all paired. Its electron structure looks just like benzene. So that one is the aromatic one. Opposite with the 7-membered ring, the cycloheptatriene cation. It's hard to draw. 7-membered ring with a plus. Okay. We're going to have 1 down low there, 1 molecular orbital, then 2 and 3, 4 and 5, 6 and 7, but I just have 6 pi electrons. So 1, 2, 3, 4, 5, and 6, all paired. If I had the radical, I'd have 1 more. If I had the anion, I'd have 2 more. Okay? In which case, both of those added would be unpaired.